If you have an alkyne, you can and you have too many pi bonds. So remember, the first bond you ever form is a sigma bond, and every bond after that, so like these blue bonds here, would be pi bonds. So if you have too many of those, then you can reduce the number by adding hydrogens. Now, because you have two pi bonds, you could just get rid of one of them, in which case you'll have an alkene. So you go from a triple bonded alkyne to a double bonded alkene. But there are two ways to have these alkenes. They could be trans, or they could be cis. To get a trans alkene, you would do dissolving metal reduction, solid sodium in liquid ammonia. To get a cis alkene, you would use hydrogen gas, but you'd use what's called a poisoned catalyst. Now, the most common one of these is Lindlar's catalyst, just named after the scientist who developed it. And Lindlar's catalyst is a combination of the palladium that you might remember from the hydrogenation of alkenes, excuse me. But it's poisoned with a little calcium carbonate, that's basically chalk, and a lead compound like lead 4 oxide there, PbO2. Now that Lindlar's catalyst is an acceptable way to write this whole catalyst. So you don't have to write all these reagents. You could if you want to, but it's acceptable to write Lindlar's catalyst with the H2 to turn an alkyne into a cis alkene. Lindlar's catalyst is the most famous and most popular of the poisoned catalysts that accomplish this, but there is one other one that you should be aware of, and that is a nickel boron complex. This Ni2b. Oops. Ni2b, this nickel boron complex. That will accomplish the same thing. So you could also have your sort of alkyne here, hydrogen gas with this nickel boron complex, and you would also get a cis alkene out of that. Finally, if you want to get rid of both pi bonds, so we had the two pi bonds to begin with, if you want to reduce both of them, then you can just do a simple old hydrogenation, bubble H2 gas through there with platinum, palladium, or nickel as a catalyst, and it'll take you all the way to the alkane. So where you had two pi bonds, you'll now have 0. So these are the 3 different ways that you can get rid of the pi bonds on an alkyne. Okay, let's see them applied to specific molecules. So in 10.9, in A, they give you the starting molecule, and they ask you what happens to that when you do 2 different hydrogenations. So I would recommend the first thing you do, because the trickiest part about this is these alkynes are linear. And it's easy, when you go from a linear molecule to a zigzagging one, it's easy to lose track of the carbons. So I encourage you to number them. So I'm going to just redraw that original molecule and number the carbons here. I'm going to have 1, 2, 3, 4, and 5. And here I'm just numbering it to keep track of things. I'm not numbering it as if I were naming it. So it doesn't really matter which end you start from here. This isn't a sort of backbone. This is just to keep track of things. So I have these 5 carbons here, and the triple bond is going between carbons 2 and 3. I also have a methyl group coming off of carbon 4. Okay, well in this first recipe, we're bubbling hydrogen gas through with Lindlar's catalyst, that poisoned catalyst. And as we saw, if you take an alkyne and you bubble hydrogen gas through with Lindlar's catalyst, you get a cis alkene. So I'm going to redraw the exact same molecule, but between carbons 2 and 3, I'm going to have a cis alkene. Now sometimes it's easiest to start with that alkene. So I'm going to redraw just the alkene, and this has to be cis. Now, it doesn't matter whether the 2 branches of the cis are going up or down. Remember, these are 3-dimensional molecules, so you can draw them 2-dimensionally in different ways. Just for space, I'm going to draw it going down. So I'm going to draw it, so here we have carbons 2 and 3. I'm going to have this 1 going down, and because this is cis, 4 also has to be going down. You could also have 1 and 4 going up. They just have to be going in the same the same direction. Okay, so that's 4. Now we have a 5-carbon chain here. And so this is our sort of circled area, and then off of carbon 4 we have that methyl group. And so that would be the product you would get from that reduction, that hydrogenation. Okay, let me take those, and now let's consider this reaction on the bottom. What if we use the same starting material, but we, instead of using Lindlar's catalyst, we just bubble some hydrogen gas through with regular old platinum. The platinum is not being poisoned in any way. Well, in that case, we're going to get regular old hydrogenation, right? If you have an alkyne and just regular old hydrogen gas with either platinum, palladium, or nickel, you don't need all three of these, just one of those, then it'll take you all the way to the alkane. Where you had a triple bond, you will just have a single bond. And like I said, probably the most confusing thing here is to keep track of the carbons. So I'm just going to number them so I know exactly how many I have and where everything is. This triple bond between carbon 2 and 3 is going to become a single bond with this hydrogenation. So I'm going to draw 5 carbons. So here we've got 1, 2, 3, 4, 5. So I'll number those. 1, 2, 3, 4, and 5. So this is like this. Notice that this triple bond between 2 and 3 became a single bond there. Off of carbon 4, we need a methyl group, so I'm going to put a methyl group coming off of carbon 4, and that would be the product you'd get. And so I'll erase this first. So you can compare those two molecules. The only difference between them is what happened between carbons 2 and 3. When we did just regular old hydrogenation, the triple bond turned into a single bond, and when we did hydrogenation with a poisoned catalyst like Lindlar's catalyst, and don't forget about the other poisoned catalyst, which we said was this nickel-boron complex, so that this is a possibility that would do the same thing, Ni2b. That turned our triple bond into a cis double bond alkene. So, in your answer, the answer is not this triple bond, of course. That molecule does not stay there. I'm just using that as a reference to sketch out the correct answer, and these would be the molecules of interest. Okay, let's try B. So with B, again, they have this alkyne with its triple bond, and we see these hydrogens here. We know we're doing a reduction. So this is we're going to reduce the number of pi bonds in our original molecule. Let's start with the one on top, and the first thing is just to copy that original molecule, use it as a reference, and let's number it so that we can keep track of everything, because it's easy to lose a carbon when we go from a linear alkyne with sp hybridized carbons that are linear to something that has a zigzag group, like an alkene or an alkane, a double or single bonded carbon molecule. So here we have these 3 carbons, and then on carbon number 3, we're going to have this 5-membered ring. Okay, well here we don't just have hydrogen, we also have this nickel-boron complex. And if you remember, that was a poisoned catalyst that was just like Lindlar's catalyst. So it's going to accomplish the same thing. It's going to turn an alkyne into a cis alkene. So we will take our alkyne and we'll have a cis alkene in its place. So I'm going to draw carbons 2 and 3 first. So I'll label those as 2 and 3. And what I know is these have to be cis. So we have a double bond there. And it doesn't matter whether the cis branches are going up or going down, they just have to be going in the same direction. I'm going to draw them going down. So I'm going to have the methyl group here going down, that's carbon number 1. And notice we've taken care of all 3 of our carbons here. The next carbon has to be a carbon in this 5-membered ring. So I'm going to go down, sure, but that is going to be one of these 5-membered ring carbons. So notice how that 5-membered ring is coming off of carbon number 3, just like above. The only difference is that the alkyne turned into a cis-alkene because we bubbled some hydrogen gas through with a poisoned catalyst. The most famous one is Lindlar's catalyst, which is a combination of palladium, calcium carbonate, and a lead compound, often lead 4 oxide. Remember that it's 4 because when you have a transition metal, you have to use a Roman numeral to say the charge on that transition metal. The charge on this lead is positive 4. It's a callback from general chemistry. So this is a poison catalyst. It's going to give us, turn our alkyne into a cis-alkene. Okay, so really the cis-alkene is our answer. This alkyne was just a reference while we were sketching our answer out. Okay, so next, what would happen if we took this same alkyne, but instead of using a poisoned catalyst, we just used a regular old nickel catalyst. So if we bubble hydrogen through with a nickel catalyst, that, just regular nickel, that is a hydrogenation, right? If you have platinum, palladium, or nickel with hydrogen, it takes your alkyne and brings it straight to an alkane. It takes both of the pi bonds away, replaces those with hydrogen bonds to hydrogens. So we can number it the same way as before, right? We have carbons 1, 2, and 3, and then we have that 5-membered ring coming off of carbon 3. And what we want to do is draw those 3 carbons just with single bonds. So let's say 1, 2, and 3. We'll number those so we can compare 1, 2, and 3. And then coming off of 3, we want our 5-membered ring. So this carbon here has to be in a 5-membered ring. So something like that. Notice how the bond between carbons 2 and 3 went from a triple bond to a single bond. So when you do hydrogenation just with a regular old catalyst, not a poisoned one, by regular catalyst I mean just platinum, palladium, or nickel by themselves, it takes the triple bond, turns it into a single bond. And so the correct molecule here would be this alkane that we have below. Now I have the numbers and the highlights there to help us guide through, but really the full answer would just be this. But try to show as much work as you can. And I strongly encourage you to number the carbons, because especially when you go from these linear molecules to molecules that are no longer linear, it's easy to lose track of how many carbons you have.